Hello, my name is Jeff Terry, and I'm here to talk to you today about how we use quantum mechanics and computational physics for experiential learning. Going to focus on using overlap integrals and how we teach that. Then I'm going to expand a little bit on just using hydrogen orbitals themselves. So first, I need to acknowledge the students of my computational physics course who did most of the work you'll see here today. Noah Samuelson, who's now a grad student at UC Santa Barbara, did the work on the overlap integrals part of the project. Varric Suzaki, a grad student at UC Riverside, and Jonas Gebre, a grad student at the University of Colorado, did all the work on the Herman-Skillman wave functions program. Computational physics involves physics and programming. It's challenging to teach. The students have different levels of preparation, and students have different tolerances for failure. And I always like to think about it as coding is like being in a murder mystery where you are both the detective and the murderer because you wrote the code that doesn't work and you have to figure out why. This quote is often attributed to Philippe Fortes, but who knows how accurate that actually is. I'm sure it's changed dramatically over time. Computational physics is very important. Almost all of us do computational work at some level. And it's important to teach proper programming, such as the computational pitfalls, the errors you can get, subtractive cancellation. I like to think about it, math is math, except when you do it with a computer. And that's one of the big problems. Things that work when you're doing work by hand don't work on the computer, and you have to be aware of that. And so those are things that we teach. We also focus heavily on code commenting, so somebody else can read the code and look at the code and understand it. And it's very important to do version control. These are all things that we teach. Why quantum mechanics? Well, there are a number of examples that you can use that touch on all the different types of math that you have to do on a computer. You have to do normalization, which involves integration. You can do solving differential equations. And the reason why I like quantum problems is there's no explicit dependence on the first derivative. That makes it easier for the students, and we find that to be very helpful. You have to do root finding. You can do matrix manipulation, all when trying to solve problems with the Schrodinger equation. So the two examples that I'm going to go through here are overlap integrals, and we do this with Monte Carlo integration. And this is a scale of problem that can be done as part of a homework during the course. And then I'm going to talk about the Herman-Skillman wave functions, which involve differential equation solving, normalization. And this is a project that takes more time. It can't be done in a week to 2 week period. So we have a 1 month long final project, and this project scale on that scale is appropriate for that. Why overlap integrals? Well, in 1986, two people from the University of Houston published an article on basic programs for calculating overlap integrals in the Journal of Chemical Education. And they reported that on a Macintosh with a 68000 processor, normalization of a hydrogen 1s orbital took 4 minutes and 48 seconds. So this is the overlap of a hydrogen 1s with a hydrogen 1s at the same internuclear spacing, which is typically 0. So when we do this and we've revisited it, we're also using a Macintosh, but we use Monte Carlo integration instead of integrating over a grid. And this allows us to do visualization and make sure the students can use good coding practices. So hydrogen 1s normalization on a Mac with a new M1 processor now takes 2 seconds. So it's a much faster process. So this on the right shows the overlap integral and its value of 1 for hydrogen 1s, with the bond axis being in the x-axis and a distance of 0 angstroms. Now, with Monte Carlo integration, there's typically 2 types of Monte Carlo integration that's done. Many people are often familiar with the stone throwing, in which you use to do things like calculating pi. And so basically you take some device you're going to throw, a stone, a paper airplane, you throw it. If it lands in the region you want, you count it. If it lands outside, you don't count it. And so the area of our pond here divided by the area of the box is equal to the number of objects we throw that land in the pond divided by the total number that we throw, which is the pond in the box. So the area of the pond is the area of the box times the fraction that end up inside the pond. The other way to do this is through mean value integration. And so with this is how we calculate the overlap integrals. We actually calculate the average value of a function by picking a lot of points, calculating the value of those points, and then multiplying by the bounds. So this gives us a very good view of the actual area. And because we're taking and calculating all the points, we can plot that to get an actual visualization of the overlap integral. Now, for our code, we instituted hydrogen s, p, and d orbitals. So we have the 1s, the 2s, the 2pz, the 2px, the 2py, the 3s, the 3pz, the 3px, the 3py, the 3dz squared, the 3dxz, the 3dyz, the 3dxy, and the 3dx squared minus y squared. Visualization is really helpful to get a picture of what's going on. And when we implemented this code, we have 2 palettes that we can visualize in, a red-green palette shown at the bottom, and a colorblind blue-yellow palette at the top. Different people see the different palettes better or worse. I usually see the red-green much better than I do the blue-yellow, but if you've got red-green color blindness, you can't see that at all. So the Monte Carlo method requires us to calculate the value of the overlap integral function throughout 3-dimensional space. And we can use these values to visualize the overlap by taking slices in the 3D space. And we're plotting a 2-dimensional slice through the 3D space that we're looking at on the left. And on the right, we're plotting the value of the overlap integral. Now, one of the reasons why I like doing this is it's really amazing how pretty 0 can be. These are 2pz, 3d x squared minus y squared overlap at a bond distance of 1 angstrom. And we can clearly see that this integral is going to sum to 0, because this green's going to cancel this red, this green's going to cancel this red, this green's going to cancel this red. But it's very pretty. You can see all the nodes in the spectrum, or in the overlap of the orbitals here. And it gives you a very nice picture of what's actually going on. And here's another example. This one is a 3py versus a 3dz squared. You can see the 2 atom positions are shown here. There's some nodal area in here and around here and all the way through there. Very pretty to get these areas of zero. This is somewhat highly symmetric and yet also non-symmetric because of the clearing out around one of the atom sites. And then you can just get incredibly interesting by mixing some of the n equals 3 level orbitals. Here's the 3py and the 3dz squared. Again, it's very easy to tell why this is going to be 0 when you look at it, because the areas of green completely match the areas of red. But because of all the nodes in the wave function, it doesn't have the simple picture that you normally think about when you're dealing with orbitals that you see in textbooks. And I think this really helps to give you a perspective on what the orbitals actually do look like. Now, you can also do things like map out the orbitals overlap versus distance. And here we have the hydrogen 1s overlap. And we find that it follows the standard textbook format. E to the negative r over a naught times 1 plus r over a naught plus r squared over 3i naught squared. This looks great. Again, it's very easy in our code to do this. You select the 1s, the bond axis. You select the initial, the final distance, and what step you want. And you click overlap versus r to plot out all these points. Now, one problem we had was we tried to calculate what the overlap of a hydrogen 1s and a hydrogen 2px orbital was. And we did this, and we found it didn't match the formula in Atkins. This was kind of perplexing to us, and so we looked at it. So when you're as old as I am, you have the 1986 version of Atkins, and I'm not sure this is still in the newer version of Atkins. But in the third edition, it was on page 403 and 404, problem 1615. And they said the analytical expression for the 1s2p overlap is r over 2a naught times 1 plus r over a naught plus r squared over 3a naught squared times e to the negative r over a naught. Now, this function did not have a maximum where ours did. It is actually much shorter than what we were calculating, and we were worried about this. So we did some work. So here we have a plot over versus r of the overlap integral versus the solid blue line, the 1s analytic. The red solid line is the 1s2p from Atkins. The yellow stars are our 1s2p calculation, and the blue stars are our 1s Monte Carlo calculation. So we had great agreement on the 1s, but we didn't have agreement on the 1s2p. And so we started looking at this and what could cause this. And so we made up our own orbital. And we were able to reproduce the red Atkins curve with this modified 2p orbital that's missing a factor of 2 in the exponent. And it's this factor of 2 in the exponent that makes it really hard to develop an analytical term for this. And so it turns out that a mistake was made, and this formula that they have listed in at least the older versions of Atkins is not correct. And so our Monte Carlo was able to detect that. Now, if we look at the code, these are things that we really focus on with the students. We want to make sure that the code is well documented. We want to have functions that are very clearly named, and so it's clear what the function does. So this is the 3dz squared orbital. It calculates the hydrogen 3dz squared orbital as a function of position. So the inputs are x, y, and z. And those are the positions of the electrons, and then you have the atom positions, X, Y, and Z. Goes through and it calculates this. It has another function that converts the XYZ to R theta phi. And finally, it returns the orbital value. So these functions are all reusable. They're housed in classes. And this is very good code written by the students. Again, and well documented is very, very important. Somebody else could look at this a year later, 2 years later, and understand what is going on. The next part of our project that I'm going to talk about is a final project, and this was calculating atomic wave functions. And this work was first done by Herman-Skillman in 1963. It was published as a large book by Prentice Hall. And they calculated the non-relativistic atomic wave functions for all elements from z equals 2 to 103. These are self-consistent Hartree-Fock-Slater calculations. And this is an example of what their Fortran code looks like. Subroutine Sheck computes the energy eigenvalue and wave function. It has variables like SNLO, roux exchange, A, EE, P, Q, T, D. It's very hard to read this code and understand. As you set up constants, Z equals ZZ, C equals SCF. That's probably self-consistent field. Many equals 200. More equals 0, less equals 0. You read through this code and it's nearly impossible to figure out what is going on. Of course, it was written in spring of 1961, modified in 1961 and 1962. But this is code that I used as a graduate student. It is actually still fairly commonly used. So we coded this from scratch. The Hamiltonian has basically a 1 electron term and a 2 electron term. It makes use of Slater determinants. And the potential has the nuclear attraction, electron-electron attraction, a self-Coulomb term, and an exchange term. So when you look at our code, it's commented, it's in classes, it's very reusable. And so here we have initialized the R mesh. The number of blocks describes the number of blocks in the mesh, which is a term from Herman-Skillman. They use this term X, and we usually think about things in terms of actual position R. And so there's an X to R scalar that converts the X values to R. Delta X initial is the initial step in X values, and the number of points is the number of points per block. Then we try and comment as it goes through, initialize the X step interval, loop for every point, multiply all the R mesh values by the scalar to convert X values to R values. And so you can follow along with what the code is actually doing. And this is very important. Here, another example, if the quantum number L is 0, the outer radius is 8 times that of the matching radius, else the outer radius is 5 plus L times the matching radius. It's important to be able to look and see things like this and understand what the code is actually doing. So when we do the calculations, here's a calculation for the carbon 1s. R value is negative 21.297. The Herman-Skillman value was 21.387 Rydbergs. So we're within 0.38% of the values that were calculated using the Herman-Skillman code. We think this is very good agreement. Now, unlike the Herman-Skillman code, things are a little different now, and we have security in computers. And so the way Macs work with security, you can't save something anywhere automatically. A user has to select, so we have the text put in a text box, and that can be saved by the user by hitting the save button. For the carbon 1s, we also have the potential as an output and other orbitals. So we have the carbon 2s and the carbon 2p, just showing the 2s because there's a radial node in the 2s wave function. Now, what's interesting is there are new elements that have been created since 1963, and we wanted to see if we could get these new elements to converge. Here's an example for element 117, which is tennessine. We started with the input potential from element 103, and we ran the self-consistent field calculation until it converged. What's nice about this is our Herman-Skillman based code runs on a Mac, iPad, iPhone, and it's available to everybody at GitHub using the address there. So here on the right, we have the tennessine 5f electrons. There's one radial node in the wave function, and the 7p down here, which is the outermost electrons in tennessine. And there are just a ton of radial nodes in this wave function. But these are also very interesting to look at and to get students to think about this, including things like what's the spatial extent of these orbitals, comparing the tennessine 1s to the tennessine 7p. The 7p electrons have a much greater spatial extent, and you can look at this based upon these calculations. So with computational physics, you can do experiential learning. It's not possible to code without making mistakes. You have to learn to find them. It's good experience for students. You can choose coding problems to reinforce a physics understanding. You can better prepare students for their future work. And if you have any questions, please contact me at terryj@iit.edu. Thank you.